All right. Hello, everyone. Welcome back to Physical Geology 1403. Lecture 4 today, volcanoes. This is a fun one.
Volcanic hazards.
And they're all fun. I love talking about all of these, but volcanoes is particularly fun. Captures the imagination. We're both fascinated and horrified by volcanoes. And I will tell you exactly why you should be even more fascinated and horrified by volcanoes today. Oh, you'll be. Oh, you will be. I'll make sure you're horrified by volcanoes by the end of today. How about that? Okay. All right, so let's do a little bit of housekeeping. The first thing that I need to do is apologize because I told you all last week or a couple lectures ago about my beautiful children, but I neglected to tell you about my wife, who I owe so much. She is so much of how I have gotten where I am, and I do her a disservice by not telling you a little bit about her. Her name is Jessica. We've been married for 9 years. She's a medical assistant. She has her bachelor's degree. She has made the selfless sacrifice of staying at home with our children for the last 6 years. But we're hoping that sometime in the next couple of years, she can get back into her passion, which is the medical field. She's from Seattle, Washington. So taking her out of the rainforest and bringing her here was probably one of the cruelest things I've ever done in my life. But she took it with good grace, and she's adapted well, and I owe her everything. So that's normally something that I would say in the first lecture, but for some reason I simply forgot this time around. And then as I was rewatching that first lecture, I realized, so I apologize to all for that. All right, second piece of business. Today is lecture 4. That means that there are 3 more in this module, okay? And 2 weeks from today, you are going to get your first exam. Week 4, you're going to get your first exam. So just start preparing mentally for that. Make sure that your notes are something that you can reliably draw upon in an exam, okay? You will be getting lab 2 today. So if you have not completed lab 1, I strongly urge you to do so that you're not doubling up on labs. When labs start getting doubled up, you start getting stressed and you start wondering if you can even do this class. Don't let yourself get in that position. Keep ahead on the labs, okay? And if you need help, why haven't you asked yet? You know, I'm here. I'm available. We can have tutoring. We can have group tutoring, okay? We can have individual tutoring, whatever you want. We can make it work. This goes to my online students as well. Okay. Let's see, what else? We have a holiday coming up. It does not actually impact this physical in-person class because we meet on Tuesdays and Thursdays right now, and the holiday is on a Monday. So we will be meeting next Tuesday. If any of you are traveling for the holiday, please be safe as you do so. If there are delays that keep you from coming back to town on time, if you get stuck in Mexico for longer than you thought, that's happened all the time for my students. Are you covering my microphone? That's not very nice. Can I hold it? Yeah, you can hold them. Anyways, just make sure you keep me in the loop on all that, okay? He's been sitting up in his vines, like coiled up, like he's ready to strike. And I only fed him on Saturday, so I think I'm going to feed him again this Saturday. He might be sending me a message. I need to eat more before winter because I don't feed him at all for about 3 months. That's when reptiles, for about that long, wherever they are, depending on where they are in the world, reptiles will go into a state of torpor. It's when their metabolism doesn't quite shut down, but it gets real slow and they don't move very long or very, very often. That's generally happens during winter. So most reptiles will enter that state of torpor. They're not used to eating, so they won't really eat. And even though I could give him food during that time and I could make him eat, that's how you get a fat, unhealthy snake. Or one that you want to get big fast so you can breed him faster. And I'm not interested in that. I want to keep him as close to his actual biological state of growth as possible. So I don't feed him for the 3 months of winter, which means I'll probably feed him a little bit extra right now beforehand. Okay. Any questions for me?
The silica, is it like found everywhere?
Yeah. Silica is everywhere.
How do you create, like, where does it come from? Because, like,
When I say silica, I most commonly am referring to that bond between one silicon and 4 oxygens, or 3 oxygens, or 2 oxygens, as the case may be, in whichever mineral we're talking about, called a silicon tetrahedron, right? The one silicon and 4 oxygens makes a silicon tetrahedron. And as we learned in our last lecture, those are the first bonds that form as a magma is cooling down, right? And so your magma is getting filled up with more and more of these bonds, which is what's making it get gummed up, right? And that's why silica-rich magmas and lavas don't flow as easily, because they're getting all gummed up by all the silicon tetrahedrons, right? So yeah, it's all over the place. Silicon and oxygen represent the 2 most common elements in our crust.
And why is there like, because I went to, it's like a desert, there's a lot of sand, and you know the crystals in there, they told me it was silica, and like,
Yeah.
it was all full of it.
Yeah, that's going to be quartz. That's quartz sand. So if they tell you it's a silica sand, that means that it's quartz. What you're looking at is usually volcanic, or igneous, I should say, broader definition, igneous grown quartz that has come from somewhere else really far away, or has been there for a very long time and is broken down slowly over time into those grains of sand. And we will talk about that process when, actually next week, when we discuss weathering and erosion.
So it's volcanic, that sand.
Most of that quartz is going to be igneous. Yeah, you can form quartz in metamorphic rock, or quartz can be left over from igneous rock in metamorphic rock. But the vast majority of it is going to be formed through igneous process. Now, as you'll learn next week, there are other ways that quartz can appear, but single unit crystals of quartz will most often be igneous. Okay. Great question. I love that when someone says, hey, I went somewhere and saw this, and now I'm curious. I love that. Keep those coming. What else we got? Any other questions for me? You may notice that I cleared away your lab ones. If you need those, or the first 12 of lab 1, I should say. If you need those back, let me know. I just wanted to make sure that y'all have enough room for lab 2 today. Okay, if there are no other questions, you know you can always stop me at any time and ask, right?
Yes, sir.
We're comfortable, we're chill, we're cool. You know that you can just stop me and ask a question.
We're tubular.
We're tubular. Wow, is that a Hocus Pocus reference?
No.
No, that's the only thing that I've ever heard tubular actually used in. Wow. Okay, now let's start off by talking about one of the most relevant volcanoes to you and me right now, and that is Mount St. Helens. Y'all ever heard of Mount St. Helens?
Yes.
Okay, Mount St. Helens erupted on May 18th in 1980. That was, oh shoot, how many years ago? 44 years ago now? Long before any of us were born, long before I was born. That was 13 years before I was born. Okay, I know that makes it really old, right? Yeah, right? So this erupted a long time ago, but a lot of people still remember it. It shook the United States physically a little bit, but extremely, it was very impactful on that generation because not a whole lot of people were expecting it. The USGS, which is the US Geological Survey, okay, part of what they do, they're a government organization, part of what they do is they monitor natural disaster threats, okay? So that includes volcanoes, they monitor earthquake-prone faults, which we will learn about, they monitor landslide zones, all of that, okay? And as this day was approaching, the USGS had noticed that there were a few signs about Mount St. Helens that may suggest it was getting ready to erupt. They knew it was probably going to erupt. There's no way that they could know when. And so they were just monitoring it. How do you monitor that? Well, we'll talk about ways that we monitor volcanoes today. But they sent someone from their, I believe it was their Vancouver office. And this one geologist, he took his camper and he was just sitting on a nearby hill watching the volcano. And as the time of eruption was approaching, he noticed some pretty drastic changes, okay? The outside of the volcano actually bulged outward by like, I think it was 6 or 8 feet or something like that. Like this big old bulge outward. And we'll talk about why that happened today. Okay, but that was one big indicator that they knew it was happening. This eruption was so powerful, it had the energy of 1,600 Hiroshima nuclear weapons. That's a lot of energy released all in one explosion, wouldn't you agree? The ash cloud went 18 kilometers into the atmosphere, up, 18 kilometers up, and spread out so far that ash fell in Oklahoma. And here, there are people here who have vials of Mount St. Helens ash. I'm one of them. I didn't collect it, obviously, but I have one. Okay, went all over. Mount St. Helens ash all over the place. Okay, a very powerful eruption. It killed 59 people, 58 of which were residents of the area who refused to leave. The USGS always issues warnings. If they think that there is a natural disaster of any kind, they will let the residents know, hey, you should vacate just for your own safety. They can't force anyone to leave, though. Okay? We actually have a discussion in this class. My online students don't need to worry about this, but for my in-person class, one of your discussion boards, the prompt question discusses the ethics of making people leave if you know that there is going to be a natural disaster. I'm curious to see what you all think about that. Okay? So, I said 58 of the people were residents. What about that 59th person? Anyone want to guess who that was?
The guy who was observing?
Yes, the USGS geologist. Unfortunately, this was a very atypical eruption. It did not happen the way that volcanoes usually erupt. They usually blow their top out, literally out the top. When you look at this before and after picture, what do you see?
It exploded the whole mountain.
It exploded out the side. Okay, not only did the top pop off, this entire side did, this north flank. Okay, and that geologist, unfortunately, had set up his camp over here on this hill. So the last thing anyone ever heard from him was a radio message back to the USGS office saying, control, control, it's happening. And that was it. They didn't even find his camper until someone found it buried in mud from the eruption for a couple of decades later. No. No. Odds are he was immediately incinerated. We'll talk about why here in a little bit later today. But regardless, this was a very powerful eruption, very interesting and very atypical eruption because it blew out that side. Now look at these before and after pictures, okay? What do you see on this hillside here? Can you tell what that is? I mean, yes, you've got your volcano and your foothills here. Do you see what this shadow is? What is that? What do we see here that isn't necessarily here?
Rocks.
There's rocks all over there.
It's hard to tell, but it's kind of like a hill or something.
Yes, what's on the hills? That's a hill. There's a hill.
Trees.
Trees! That's all a forest. And now after our eruption, no forest. Blasted to oblivion by that eruption. Like I said, 1,600 bombs, right? Nuclear bombs. A lot of energy, blasted everything away. Okay. This is Mount Tambora in Indonesia. You ever heard of Mount Tambora? Mount Tambora erupted in 1815. This is what we call a supervolcano. Have you heard that term before, supervolcano? What do you typically hear that word supervolcano applied to? Yes, it's a very big volcano. But which one in particular do you usually hear supervolcano applied to? No? Oh, this is actually kind of good, because if you don't know, then you probably haven't been the victim of a whole bunch of those terrible non-science news stories. Yellowstone. Yellowstone is a supervolcano. That is true. Okay, I'll talk more about Yellowstone later. Yellowstone and Mount Tambora are the only two active supervolcanoes on our planet. There are actually 26 of them, but all but these two are either inactive or extinct. We call them supervolcanoes because when they blow up, they affect the entire planet. Mount St. Helens affected a substantial portion of the northern hemisphere. Okay, the ash went all the way halfway across North America, went way up north, went out in the ocean a little bit. Okay, it had a substantial effect on North America, not a supervolcano. A supervolcano will affect the entire world. In 1815, when Mount Tambora erupted, it sent clouds of ash into the atmosphere so big that it killed crops in New York. A volcano that erupted in Indonesia sent the world into what we call a micro ice age. Think about if a year went with only 2 or 3 weeks of summer, and then you're just right back into fall and then an extended winter. That's what happened. There were famines across the entire world. It was not good. Lots of people died because a volcano in Indonesia went off. A supervolcano, one with enough power to create such an ash cloud. Okay? Yellowstone would do the same thing and has many times in geologic history. Okay? We'll talk more about Yellowstone later, but just wanted to let you know, supervolcanoes are a thing. Now, why do volcanoes erupt? Anyone want to take a guess?
Pressure.
Pressure. Tell me why. Why would pressure make that happen?
Too much heat. Like
There are a couple of different types of eruptions we're going to talk about today. The first one I just showed you, that's more of an explosive eruption. This one, I call this a spitter. It's not even really blowing up. It's just kind of like spitting out lava, right? Obviously, in both cases, there is some kind of pressure pushing this material out. Just one is more violent than the other, okay? You'll find this more typically in places like Hawaii. Mount St. Helens and Mount Tambora, those were examples of that more explosive type, okay? We'll learn today why there's that kind of variety. The controlling factor, the biggest one on how explosive your eruptions are, is the viscosity of your magma. Someone remind me what viscosity means. How thick it is.
Resistance.
Yes, resistance to flow. Excellent. We got there. Good teamwork. Okay, resistance to flow. So here we have some water. Highly viscous or non-viscous?
Viscous.
Non-viscous. And here we have some corn syrup. Highly viscous. Okay. Oopy goopy, right? Okay. Sorry, I have children. All right. Now, the biggest things that will determine how viscous your lavas and magmas are is your silica content. We talked about that before. Why would silica content control viscosity? Because we're forming more what? This is what we were talking about before.
more bonds.
Bonds of
Tetrahedron.
silicon tetrahedrons. More silicon tetrahedrons means more bonding. More bonding means more viscosity because those bonds are gumming up that liquid, that fluid. Okay? So if I have a lava or magma that has more silicon in its composition, I'm going to end up with more silicon tetrahedrons, and it's going to get more viscous faster. Okay, so silicon, number one factor for viscosity. Also, there is heat. Why? Well, because if you have more heat, less of the silicon tetrahedrons will form in the first place. Okay, then you need to drop the heat enough for those bonds to form at all. And then also the amount of volatiles. What do I mean by volatiles? Dissolved gases. Okay, why would that matter?
What was the question?
What dissolved gases. What do I mean when I say dissolved gases? Steam is one of them. Let's watch these two clips here again. And tell me what you see in common between these two liquids. Bubbles. They both have bubbles. What are the bubbles doing in the water? Rising. What are the bubbles doing in the corn syrup? They're staying. It's too viscous for the bubbles to escape. So they just build and build and build and build. What happens if you get too many bubbles in a liquid in an enclosed environment? Yeah, that pressure builds and builds and builds until pop, right? So, in a nutshell, why do eruptions happen? You get magma coming up from the mantle, whatever has caused it to form into magma, like we discussed in our last lecture. Okay, any of those reasons, you get your magma here. It comes up through the crust. As it goes through the crust, it goes through Bowen's reaction series. It starts to differentiate, right? It goes through Bowen's reaction series, changing its composition, gradually becoming more felsic, aka richer in silica, aka more viscous. Okay, so as it finally reaches near the surface, you've got a fairly viscous, highly felsic magma a lot of the time. Okay, then as those bubbles start to form in this zone of lower pressure, the pressure inside of the magma chamber starts to build. And as the pressure inside of the magma chamber starts to build, eventually a threshold is crossed. And at some point, the number that equals the pressure, whatever that pressure is going to surpass the weight of the rock on top of it. And when that happens, pop goes the cork, and you have a volcanic eruption. Okay? Now, watch this. What is the first thing that comes out when this cork gets popped? What was it? Gas. In this case, carbon dioxide. There's a lot of other gases that come out in a volcano, but it's the same principle. You have a confined vessel inside of which you have a highly pressurized fluid, and as soon as you release it, pop that cork, or the rock on top, the cap of rock on top of the volcano is no longer sufficient, and it pops off, all of those gases surge out, and with them comes all that fluid, all that magma. Okay, that's what causes a volcanic eruption. So why do we have those two types of volcanic eruption? Why is one more violent than the other? Here's a logic train for you. Follow it. Ride those tracks. Tell me where it takes you. Why would we have two types of eruptions, one more violent than the other? Say that a little louder. Not so much if it's in a glacier. I do. I know what you're saying. The type, excuse me, the type of crust that your volcano is in absolutely plays a role on this, and we will discuss that here in a minute. But before you even reach that point, we're talking about something a little more fundamental. What did we just talk about determines the viscosity of magma? Silica content, temperature, volatiles, all of that. Okay? Right. And in a more viscous magma, what do the bubbles do? They can't move very far. And so as more bubbles remain where they are, but more bubbles continue to form as your magma is cooling off, what happens to the pressure in your magma chamber over time? It increases, it builds, until finally what happens? Yeah. You get a boom. So what about if you have a magma that is low in silica? What kind of viscosity do you have? Yeah, it's going to be non-viscous, pretty non-viscous, right? Those bubbles are able to escape. And because those bubbles can escape, you get very non-violent eruptions. This is why we have those two types. You have Violent eruptions like Mount St. Helens, kaboom, because it's formed, that pressure builds in a magma chamber that has a lot of pressure building it. It has a lot of gases, okay? Then you've got your more Hawaii-style eruptions with magma that is very fast and runny, okay? And because it's fast and runny, those bubbles can escape out. And as those bubbles escape out, you've kind of got that spitting lava effect, okay? Very rarely do we get a violent eruption of any kind out of Hawaii. Every now and then you'll see a lava fountain where it's just like, but never kaboom with a giant ash cloud, okay? That's not the kind of eruption that volcanoes in Hawaii have and in similar circumstances, okay? We'll talk about why the magma in those places is non-viscous, why it is not rich in silica here later today. I wanted to show you, oh, bless you. This is just kind of an example of what I was just talking about, your more explosive eruptions like that. This is about as violent as Hawaiian eruptions ever get. That's called a lava fountain, okay? Most of the time when volcanoes like Hawaii erupt, when we say that they erupt, what really happens is their magma chamber kind of overfills from its source down below in the mantle. And then because it overfills, it just kind of like oozes out onto the surface of Hawaii and builds out those islands a little at a time. This is drone footage of a volcano that erupted last year in Iceland called Mount Fagradalsfjall. Who wants to say that with me? Fagradalsfjall? Good job. All right. Look at this lava. How fast is it going? That's pretty fast. What we are looking at here is a non-viscous flow. That's not terribly explosive. There's no giant ash cloud, right? I know. What an amazing shot, isn't it? Love that shot. They flew hundreds of drones over that eruption trying to capture that footage, and this is the only one that I'm aware of that made it. The guy that took that footage, I have to give him credit, Bjorn Steinbeck. Fantastic drone. He does so much images, so many fantastic images of volcanoes and glaciers and whatnot in Iceland. I love his work. He's on Twitter. You can follow him there and see his work if you'd like. Huh? Yeah, wouldn't be awesome? Okay, so this is a pretty fast-moving flow right here, right? Mafic or felsic, would you guess? It's probably pretty mafic. Yeah, probably somewhere on that spectrum. Yeah, good call. Okay, so of all the material that gets extruded at the surface, and by that I mean what turns into lava, it gets pushed out on the surface, therefore it is lava. About 90% of it is mafic. 90% of it is mafic. Why would that be the case? Mafic lava makes mafic rock.
It has no low content of silica.
It does have silica. All silicate minerals are going to be based off that silicon tetrahedron. It just has less of it. Okay? But the point I'm trying to get at here is why so much of all the material that gets pushed out on the surface would be mafic. Most of our planet's surface is covered in water, ocean. What's under that ocean? What kind of crust? Oceanic crust. Oceanic crust, what's the #1 most common igneous rock in the ocean crust? Basalt. Okay, so this is where all of that is coming from, okay? So because so much of our Earth's surface is covered in ocean, continental crust is under the ocean. Most of the continental crust under the ocean is basalt. We get a lot of mafic material pushed out on the ocean floor. That's what I'm trying to get at here, okay? About 9% of it is intermediate, and about 1% is felsic. Why would there be such a small amount of felsic material that gets pushed out on the surface?
More viscous.
Exactly. It's more viscous. What does that mean?
It doesn't flow that much.
It doesn't flow. It usually takes a lot longer for us to get there. Well done. Okay. Felsic magmas and lavas don't move very easily. And so if there's enough pressure to push it out to the surface, how far is it going to go before it just can't move anymore? Not very far, right? So there are some felsic flows, but very few, because it is so viscous by the time it gets up here, it can't go very far at all. Okay? That's why only 1% of all of the stuff that gets pushed out is felsic.
30 kilometers an hour.
30 kilometers an hour. Yeah, that's the fast flow. I think I said this last time. I hope you've got a bike, right? You are not running away from this, at least not for very long. Okay? You're pretty fast? Yeah, what's your fastest mile?
Anyway,
It's not fast enough.
it might be,
Yeah.
I might be faster than Usain Bolt.
You might be faster than Usain Bolt. You know what? I won't know unless I see you do it. So I guess we have a Schrodinger's cat situation here. You are both faster than Usain Bolt and not faster than Usain Bolt until I test you.
Yeah.
Sorry if anyone doesn't understand the reference.
Equally correct and incorrect.
Yes. Okay. All right. Who wants to learn some fun new language words? Let's learn some Hawaiian.
Yay.
Yay, we're going to learn Hawaiian.
Hello.
Okay. This is a kind of igneous rock, which is called a'a. Say it with me. A'a. A'a. Why is it called a'a? Well, if you're Hawaiian and you're walking around barefoot and you step on this, what do you say? I'm kidding. That's not the reason, but I love saying that joke. I actually had a Hawaiian girl in here one time. She thought it was the funniest joke ever. She just kept laughing. All right. I used to live in Hawaii. I lived in Hawaii for 3 years, so I feel like I'm justified in making a little fun. So we have this rock here, a'a. A'a is very chunky and sharp and blocky and kind of sharp, and it just kind of breaks apart into this sort of I don't know. It's this jagged, chunky block. That's really the best word I can use to describe it. Now, a'a is formed when you have a fast-moving, so non-viscous, mafic flow on the surface, and it cools off quickly. Huh? Not immediately. Remember, we get obsidian if that happens. But it's low temperature now, okay? This is what happens at the low temperature end of a mafic lava flow. You make a'a, okay? I'm going to pass that around. There are fields of a'a all over the newer islands of Hawaii. Any of you ever been to Hawaii? You have? Did you go to the Big Island or Oahu? All of them? Nice. I didn't make it to all of them. I went to the Big Island a few times. I went to Kauai a few times. I lived on Oahu. Loved it. But the Big Island is the one that has the most recent volcanic activity. Here's a little fun fact about the Hawaiian Islands. The big one is the most recent one. The ones at the far end of the chain, those are the oldest ones. Okay, because as time goes on, they break down, they become smaller. A lot of people think the bigger ones are the older ones and the smaller ones are the new ones. It's the other way around. Okay, the Big Island of Hawaii is actually only about 2 million years old, I think. 2 to 3 million years old, something like that. Anyways, so that's a'a. Now, what happens when you have that same flow, but you're probably closer to the source? It's hotter material. It's still cooling down, but it hasn't moved as far and lost as much temperature over time. It hasn't quite reached that point of being where all the bubbles are forming like that, making that chunky block. When you cool down from a high temperature flow and then it cools off pretty quickly, you get pahoihoi. Say it with me, pahoihoi. Okay. And it makes a sort of smooth, ropey textured igneous rock. If you looked at that a'a, someone tell me, is that mafic or felsic? Mafic. Why is it mafic?
Went down more.
Tell me why you think it's mafic. Do you think that's mafic?
I wouldn't believe so.
Why? It's got bubbles, but that makes it vesicular. That's a texture. We're talking about composition. It's mafic. Why? No, it came from magma. Remember, when we're talking about composition, that's the minerals it's made out of. The minerals we talked about are separated into light and dark silicates. Are you going to say that is made from more light silicates or dark silicates? Dark silicates, and there it is. Okay, the percentage of dark silicates in there is an easy way to identify if you're looking at a mafic or felsic composition igneous rock. That is clearly a mafic igneous rock. I see nary a light mineral in there. What about this one? That's actually just residue from when a student dropped it one time.
Oh.
Yeah. Here, let me show you that side. How about that? This is clearly also mafic. It's about the same color. These come from the same flow. However, this formed while the flow was still really warm, still really hot, probably closer to the source. It went from high temperature to forming this pretty quickly. That is further along, probably further away. Our mafic flow has lost temperature. It's as it's moving away. It's becoming harder to move. You remember that video I showed you last time where you heard the sounds of breaking glass? That was rapidly becoming an ah-ah flow. That's about what I'm talking about. Okay? Whereas pahoehoe, look at this. This is a field of pahoehoe. This lava is still running and moving underneath of what is forming on top. These are pahoehoe. You can see that sort of ropey texture forming there. Okay? This is ah-ah. This is probably a flow very similar to that, just further away, where it's not as hot anymore, okay? By the way, these guys are insane. It is so hot next to a lava flow. That's like a million candle power right there. Like, they should be wearing heat suits. Even if you're in a heat suit and you're standing next to a lava flow, it's still so hot. Okay, so, pahoehoe, let me pass that around. I have no funny joke about that name. Okay. What are some of the features that we can see that form in or around volcanoes? Well, some of the more common ones. Lava tubes. A lava tube is what happens when you have a lava flow that is either moving through the ground or in some sort of confined area on the surface. Okay, so like you have a flow on the surface, maybe it found its way into a stream bed or something. Okay, so you've got your lava flowing through the surface through some low area. Okay, now while it's still really hot, what's going to happen? It's moving quickly, but the outer surface of your flow is still going to cool off and crystallize. Exactly. And you get a sort of crust that forms around that flow. It makes a sort of tunnel. Okay? The outside of your flow has cooled and crystallized and formed a sort of tunnel. And through that tunnel is still rushing very hot, very fast magma or lava. Okay? So we're at the surface now, or near the surface. Okay? So it's rushing through there. Now, as time goes on, your volcano starts to die down a little bit. It's kind of blown its gasket. It's done. There's not a whole lot of pressure left. That flow is going to slow down, and it's going to start cooling down. And as that happens, you aren't going to form a pahoehoe type rock. You're going to form a more ah-ah type rock, that chunky, blocky stuff. So you have essentially a smooth exterior tunnel wall inside of which is a whole bunch of chunky, blocky lava rocks. What happens the next time that volcano starts to act up a little? It starts to burp out gas. Where's that gas going to go? Probably down through the same paths that it was allowed to go before. This tunnel being one of them. And when it does, when that gas comes rushing through that tunnel, you know what it's going to do to all that loose rock in it? It's going to shotgun blast it out the other side. It's going to push all that rock out. And that's how you can end up with a lava tube. You end up with these empty lava tubes. You can actually go on lava tube tours in Hawaii. It's pretty fun. They're pretty cool. Okay. Then you've got block lavas. A block lava is what happens when a felsic or intermediate lava flows across the surface. Okay. Again, it can't go very far because it's pretty viscous. But when it does flow and then it does cool down, it tends to you don't generally get a flat layer of that rock. Okay, especially for the more felsic ones. You tend to end up with a field of broken, shattered rock because as that lava is cooling down, the pieces, like it tends to separate itself from the pieces, kind of like how mud cracks form. You know how you've got mud? Let's say I filled a cookie sheet with mud and then I dried out that mud over a few days. What's going to happen? I'm going to form cracks in those mud as the moisture leaves, right? Think of it as like that. As this lava is cooling down, it's going to contract a little bit, and the pieces are going to separate from each other. So you ended up with a block lava field like that. And then pillow lavas. These will form underwater when you have a fast-moving, usually mafic, high-temperature lava that gets pushed out of an underwater source of magma, and it gets pushed along the bottom of the ocean. It's going to do this. As it's moving, it is instantly being quenched on its outer surface, making this sort of pillow shape that is constantly pushing outward as new lava is making its way through that tunnel. You see how I call it pillow lava? You guys ever do those 4th of July like firecracker toys where you light them and it's like a worm that's constantly growing out of itself? It's like, shh. It's kind of like that, isn't it? Yeah.
Like going through the dirt or like underwater?
Yeah, this is underwater. This image was taken underwater. This video was underwater. So you've got a lava flow underwater, but the outside of that flow is instantly getting cooled off by the water. That's what's making that crust on the outside. But that crust is also constantly being pushed aside by the lava pushing in through behind it. Okay, so that's why it's kind of curving around and making that smooth sort of tunnel, pillowy shape as it moves down through the bottom of the ocean. How are we doing? Any questions?
Nope.
All right. Now, in general, there is about 1 to 6% of the total mass or of your magma is going to be some kind of volatile. Most of that is going to be water vapor. Now, on the high end, where you have lots of volatiles, you're going to get a very explosive eruption, and it's usually going to happen more often. When you have less volatiles, less explosive eruption, probably a little less often. Okay? Those volatiles, those gases, are going to be the main cause for what builds that pressure in your magma chamber. During an eruption, a single day of an eruption, like a major eruption like Mount St. Helens, thousands of tons of gas are released. Okay? CO2, water vapor, sulfur dioxide, all of that. Nitrogen. Do some of those gases sound familiar to you, by the way? Why do they sound familiar here together?
See them all the time.
Where? Where do you see them all the time?
Wait, which one?
Nitrogen, carbon dioxide, water vapor,
These are like clouds.
our atmosphere. This is a little bit of a spoiler for 1404, but our current explanation for our atmosphere, why we have an atmosphere at all, is because of the billions of years of volcanic activity that our planet has had. As these gases form in the igneous process and are spat out of a volcano, they stayed in proximity of our planet, drawn here, kept here by our gravity, and have remained here. And now we have this envelope of gases which you and I have evolved to breathe. Okay. Now, I mentioned this word before, pyroclastic. Pyro means fire, clastic means fragment. Pyroclastic rocks are those igneous rocks that are made from a volcanic eruption. Remember when we were learning about igneous textures and I mentioned that one of those textures was pyroclastic? I told you then, and I'll remind you now, that pyroclastic rocks are not made by the crystallization of magma. They are made during a volcanic eruption. This is a bunch of ash and shattered fragments from a volcanic eruption that got compacted together and made this unit of rock. That is what a pyroclastic rock is. And we differentiate them from each other based on the size of whatever's in them. For example, ash is anything under 2 millimeters, and that tends to make a type of rock called a welded tuff, which looks like this. Okay, this is a welded tuff, Tuff. That's pretty much just volcanic ash that fell right during an eruption when it was still super hot and got fused together. Then you can get lapilli, which most people refer to as cinders. Okay, so those are going to be kind of your chunks, like what's in this right here. Okay, this is your breccia. Okay, this is a volcanic breccia. But you see those fragments in there? Those are cinder-sized pieces, also referred to as a lapilli. That's a Greek word. Okay, I believe that's Greek. I'm probably just mispronouncing it. But anyways, that's that size, okay? 2 to 64 millimeters. Anything larger than 64 millimeters, we refer to that as a bomb or lava bomb, you may have heard them called. These are hot, semi-melted fragments of rock that have been blasted away from a volcano so fast and are now falling down through the atmosphere back to Earth, that they actually take on a sort of streamlined aerodynamic shape. Like this. It almost looks like a sort of teardrop or raindrop shape, because as it was screaming through the atmosphere in its half-melted state, it got turned into that shape. It got kind of molded into that shape by its passage through the atmosphere in the same way that a raindrop takes that shape as it falls through the atmosphere. Okay? That's a bomb. Lava bomb. Yes. Mm-hmm. Well, at the speeds that they hit, might as well be a bomb for what it would do to you. Okay. I told you about pumice last time, right? Someone remind me what pumice is.
It's the rock that you can pick up at Walmart, or you can. Like,
Yep. We often use it to exfoliate skin. What else?
Like it had a lot of bubbles.
It's got a lot of bubbles. Why?
It was like the outer, like from the outer layer, like of a rug, like
Outer layer.
like from the middle to more bubbles. You get it? Hard to explain.
Yes, it is hard to explain. Let me explain it this way. Do you remember when I showed you that video image, or that video of me, of someone popping the cork off of that bottle? What was the first thing that came out?
Gas.
Gas. What was the next thing that came out?
Foam.
Foam, which is the same fluid, the same liquid that's down there in the bottle, but it's been filled with so much gas that some of that liquid is coming out along with the gas. That's pumice. This is essentially from the lava, from the magma down there, but it's been pushed up and cooled so quickly while it was filled with so much gas that it's full of all these little gas holes, these vesicles, right? This will float on water because it's full of so many holes. That is what happens when usually a felsic or intermediate magma goes through that process. But what happens for a mafic flow, or mafic magma, excuse me, when that happens? Well, you get something very similar, but made from something significantly higher in dark silicate minerals. We call this scoria. This is the real scoria. What they call scoria in the oil field that they put down on oil pads is not scoria. Okay.
So the actual scoria.
This is actual scoria. Okay. You can see the similarities here, except for one big one. The color, the compositional difference. What kind of magma it came from. Very similar processes for what made them. Okay. highly aerated, lots of gas, but different composition, lots more dark silicate minerals in here from that mafic magma. So darker, also denser. This will not float, at least not to the same extent that pumice will. Okay, let's talk about volcanoes. I guess you could say the anatomy of a volcano. Okay, so our volcanoes generally have a sort of cone-like shape. That's a natural consequence of what the volcanic process is. That's what an eruption does. Well, eruptions will blast material out. It'll disperse. Most of it will disperse closer to the source. Less and less of it will disperse further away from the source. And so you get a buildup of material closer to the source and less further away. And so you naturally build this cone shape to varying extents depending on the type of volcano, which we will discuss next. Okay. So then we have our conduit, which is this passageway up through the crust from your magma chamber down below. Okay. This conduit comes up, and where it reaches open air, we call that a vent. Okay. That vent lies inside of a depression on the top of the cone called a crater. You've probably heard that term before. A crater. How many of you have ever been to Yellowstone National Park? No one? No. Well, you should. If you go to Yellowstone National Park, you are inside the crater of that volcano. The crater of Yellowstone volcano is 15 kilometers wide. And that's why we call it a supervolcano. Okay. Then we've got a few other things. For example, every now and then you'll get what's called a parasitic cone on the side. That's when a sort of, there's a branch off of magma from the main conduit. You get the sort of side conduit. It just kind of chews its way through the volcano and then pops out the side. Okay, so you can have flows of lava coming out the side during an eruption. And then fumaroles, which are not on this image, but occur around the perimeter of a volcano that is very active. What happens is, because there's so much magma near the surface, it heats up the groundwater, and that groundwater escapes as steam, and that steam will release other gases. And so that's actually one way that we monitor volcanoes to see if they're getting ready to erupt or not. We'll measure gas output from steam vents around the volcano, things like that. Fumarole. Huh?
What's a volcano that's close to erupting?
What is a volcano that is close to erupting? Yeah. That's very hard to say. There are about 6 or 7 in Alaska, in the Aleutian Islands, that are in a constant state of, is it gonna, is it, no, it's not. It might today, right? That's probably the most active place as far as you and I are concerned that are close to us, right? Do you have a question?
Wasn't there one that erupted in Maui that took out the whole, messed up everything?
You're talking about Tonga.
Yeah, that one.
Yes.
Tonga?
That was Tonga. Yes. No, there are no active volcanoes on Maui. The only active volcanoes in Hawaii are on the Big Island and on the new island that is forming off the east coast of the Big Island. But in Tonga last year, there was a very violent underwater eruption that sent a small tsunami through their capital and covered their island in ash, which was very difficult for them because tourism is their main financial income. So, and no tourists are going to go visit an island covered in ash, and so they're still recovering from that. Yeah.
And then there was I heard a volcano that got filled up with water, and then it exploded.
And then it exploded.
And that's water. I heard something like that, like in South America or something.
Like this is something that happened recently? I haven't heard of any volcanic eruptions in South America recently.
No, I don't think it was recently.
Okay. Yeah, I'm not familiar with what event you're talking about. Volcanic craters get filled with water all the time. Case in point, Crater Lake. Crater Lake in Oregon is what is left of a giant volcano that blew up so powerfully, it basically destroyed the volcano. I'll talk about this more later. Okay, and now it's a lake.
Is that what we count as an extinct volcano then? Or like
Yeah, as far as we know, yeah. Okay, I'll talk more about Crater Lake here in a little bit.
It's just a giant magma pool underneath there, huh?
Huh?
It's not just a giant magma pool underneath there, huh?
Under Crater Lake?
Yeah.
I'll talk more about that in a minute. I'll answer that question. Yeah.
Where did you point out the fumaroles?
Well, they're not on this image, okay? But they'll be around the perimeter of your volcano, okay? As the groundwater in the area is heating up because magma is approaching the surface, it's going to cause steam and other gases to escape. That's a fumarole. Any other questions before we keep moving? We're making good time today. But please still ask questions if you need. Okay. This is another image of Fagradalsfjall in Iceland. What do you notice in this picture? Describe. Huh?
The people are awesome.
Oh, yeah, there's lots of people. That's a good observation. What are all those people doing there?
Waiting for it to flow.
No, it's actively erupting. You can see this is like a still shot, but there's magma or lava flowing out, and this is a lava flow right there. Those people are there because this is Iceland. And they're on their lunch break. This eruption actually only happened, I think it was only like 15 kilometers from the capital, Reykjavik. Okay. So, yeah, on their lunch break, people just went to go watch the eruption. That's Iceland for you. Huh?
To cook their lunch.
If you got close enough to cook your lunch, you'd have cooked yourself already. Yeah. You don't want to get close to a lava flow.
We'll be careful.
You'll be careful. All right. All right. Yeah. And just make sure that your hot dog is on an extra long stick. All right. Yeah. But okay. Let's describe this volcano. Describe it. What do you see? What shape does it have?
That's like a ring around it.
It's vaguely cone-ish, right? It's a cone, just like we talked about. Up here, so coming up from underground, there is a vent or a conduit right here filled with magma. And then it reaches the top, and whatever bubbles are making their way up through that magma from the chamber are causing it to kind of spit out the top here, and then it's flowing away, okay? Just like we saw in our diagram. Now, there are three types of volcanoes that we're going to learn about today. A shield volcano, a composite cone, and a cinder cone. Shield volcanoes are by far the largest. Anyone want to give me an example of shield volcanoes? Can you think of one? I've talked about two today already. Shield volcanoes are very large and wide. Hmm?
What, the Indonesian one?
Tambora?
Yeah.
Not really. Tambora in its current state at least is a very tall one because it technically is at the bottom of the ocean and comes up. It's on an island.
Yellowstone?
Yellowstone is a shield volcano, yes. Also, all of the volcanoes on Hawaii. Those are all shield volcanoes as well. Okay. Cinder cones, you probably have seen and just didn't notice. We've actually had historically a lot of cinder cones in West Texas, down by Mexico, in New Mexico. If any of you ever flown into Arizona, like flown into Phoenix Airport, I guarantee you've seen cinder cones from the air. You just probably didn't know what they were at the time. Okay. And then composite cones, those are also called stratovolcanoes. Those are by far more notable. That's your Mount Rainier, Mount St. Helens, Mount Baker, all of those, okay? All those big, tall, dangerous-looking ones. So let's start off by talking about shield volcanoes a little bit. These are very low and flat and wide. And I say low because I mean it's just literally almost nearly flat layer built upon nearly flat layer, that have spread out a very far distance. Why do you suppose this lava was able to spread out a very far distance? Okay, so the lava went onto a flat area and spread around. But what else would be necessary for it to be able to flow away? What do we call something's capacity for flow? Viscosity. It had to be very low viscosity for it to flow that far, right? Which means what kind of composition did it probably have? Mafic. Good. We're looking at the result of mafic lava being pushed out at the surface, and because it is non-viscous, it can flow far before it crystallizes enough to stop moving. Shield volcanoes are made from mafic lavas. Okay? The entirety of Hawaii and Iceland. And yes, a substantial amount of the Yellowstone volcano and the area around it are made out of mafic rock, like basalt. Okay? Now let's talk about cinder cones. Cinder cones are the smallest and generally least dangerous, but they can pop out of nowhere relatively quickly. Okay? There's usually not even any lava associated with them. They usually show up quick and die off pretty quick too. And it's usually just because some magma got close, but not really, there wasn't really enough of it to make a bigger volcano. It just kind of made a volcano, and then whatever the source was just kind of died down or cooled off. Okay? So just to give you an example of how quickly these things can show up. There's a story from Paracutin, Mexico. Apologize if I'm saying that name wrong. Paracutin? Paricutin. All right, I'll try to remember that. Thank you. Paricutin, Mexico. Back in the 40s, I believe it was, there was this farmer who went out into his field and noticed that in one of the fields near his home, there was some steam coming from a crack in the ground. He didn't know what it was. He was like, well, I got work to do, so I can't deal with this right now. I'll think about it later. So he went out into the fields further from his house, like the far fields, and he stayed the day working out there. And throughout the day, he heard what sounded like thunder, but the skies were clear. And so he just kind of dismissed it. Okay, whatever, what's going on? At the end of the day, he went back home and he found that this crack that had been spitting steam before was now a giant pit filled with fire. And he couldn't find his family anywhere. The farm was abandoned. So he went to the nearest town, Paricutin. Okay. He found his family there. They had run away because they were rightfully afraid of whatever was going on there. And they abandoned the town. They evacuated the town, which was good because over the course of the next year, that cinder cone, it became a cinder cone volcano. It grew 330 meters. Yeah, in 1 year. And you can actually find pictures online of that town, a substantial amount of that town, with lava flows running through it. This particular one did have lava. It's not common, but they do sometimes, and this one did. You can find pictures of the church, the local Catholic church. It's almost like a small, not cathedral, but like it's one of those nice stone churches that like have a lot of history, you know? But like all that's above the lava flow is the steeple. Yeah, so in 1 year, this entire area got totally ravaged by the appearance of this one cinder cone. So they can pop up, but that cinder cone was dead, I think, the next year. Totally inactive and has been ever since. Okay, so they come fast and they're gone fast. That's kind of cinder cones. All right. Now, as potentially dangerous as that sounds, that's nothing compared to our next contestant, composite cones, also called stratovolcanoes. Now, why are these the most dangerous? Anyone want to take a guess? They do die. When you say die, first of all, there are a few terms we have, okay? Active means this thing could erupt at any time. It has magma, a magma source, and it could just go. There is inactive, which means that it has a source down there, but as far as we can tell, none of the magma is near the surface. There's the potential it could be in the future, though. And then there is extinct, which is its magma source is totally depleted or solidified. That's what extinct means, okay? So, why are these the most dangerous?
How are they built?
Because of how they're built, not so much.
Well, if they're in the Ring of Fire, wouldn't that mean they're coastal?
They are coastal. And how much of our population lives on the coast? A lot. In the United States, I believe it's about 50%, right? And there's not volcanoes on every coast of the United States, but there sure are on the West Coast, right? And how about on the West Coast of South America? And how about on all those other coasts and all those other islands, right? Where there's all these volcanoes. How about the entirety of the nation of Japan? Okay, that's all volcanoes, okay? So a lot of people live around these volcanoes. Also, why are they the most dangerous? There's another reason. It wouldn't even matter if people live near these things except for this reason. The viscosity. These are fed by felsic and intermediate magmas, meaning that they are very
Low.
high viscosity, meaning that they are very. We're not talking about lava flows. The volcanoes, when they erupt, are very
Pressurized.
Oh,
kaboomy. Yes, they're explosive. Okay? They go boom big. All right? So when that happens, that puts the people around them in a lot of danger. If not for that fact, it wouldn't matter if people lived around them, right? So a lot of them appear in the Ring of Fire. Why? Well, because as I mentioned before, the Ring of Fire is around the Pacific plate because there are so many plate interactions in that area, okay? So some are subducting, some are scraping past each other, some are diverging. And at every single one of those sort of boundaries around the Pacific plate, there are these volcanoes forming as a result of the friction or the decreased pressure or whatever the case may be, the introduction of water into the mantle. So there's lots of magma coming to the surface around the perimeter of the Pacific plate, okay? So there's lots of these composite cones threatening all those people all the time. Let's talk about some of the dangers associated with being near a composite volcano. First thing is a pyroclastic flow. A pyroclastic flow, and by the way, this is the part of the lecture where I teach you how to have nightmares about volcanoes. And yet still also love them. I love volcanoes, but I would never want to live right next to an active one. And I have. I'll get to that in here in a minute. I can't say that I never would. I'm torn. All right. Pyroclastic flow. When that volcano erupts, when you pop the cork off that bottle, remember what that first thing that came out was? The gas. So when a volcano erupts, that gas also comes out, that first burst of gas. But guess what? It's hot. It's extremely hot. I'm talking like 400 degrees Celsius hot. Okay?
Whoa.
Yes. Hot. That's like stuff is still melted down there hot. And because it is that hot, it expands at an extremely rapid rate. It is highly pressurized, extremely hot gas. And it expands extremely quickly, taking with it ash. Okay? And so we've got hot gases and ash expanding at up to 200 kilometers an hour from this eruption. You ain't getting away from that. This is usually what kills people near the volcanoes when it erupts. Anyone nearby gets this treatment. Okay? And here is a video for you to think about tonight when you're trying to sleep. Yeah, run. Keep going. Yeah, no, he eventually did get smart and got in the car. This is actually pretty slow. That's not moving at 200 kilometers an hour. That's slower. They got away. The only reason why it wasn't going faster than that is because this is a hill, and then on the other side of that hill was the volcano. So it erupted, and the pyroclastic flow had to go over the hill and then back down the other side to get into this village here. This is in Japan. Okay? So they did get away, thankfully, right? But only because that hill saved them.
So that cloud right there.
That's the pyroclastic cloud. That is so hot that every tree, person, building, telephone pole, train, everything in its path gets instantly incinerated. That's a pyroclastic cloud.
That's wow.
Mm-hmm.
I always looked at them in the like movies and like the different demonstrations. I was like, I mean, it's just a regular old cloud.
I'm glad you brought up movies because now I'm going to talk about one. Have you guys seen the Rings of Power TV show? Yeah? Who said yeah? Did you like it? I liked it too, except for one very, very, I don't even know the right word. You know, at spoilers, I'm so sorry for anyone if this is spoilers. You know what I'm talking about at the end when the volcano erupts? And the pyroclastic cloud comes and sweeps into the village. And she's just standing there like, oh, this is so sad. Oh. I was like, what is this? Yeah, you're ash right now. Everyone's ash. The village is ash. And then you come back the next episode and a few things are on fire, but everyone's okay. Yeah, she's just standing there in the open. Her hair's not even singed. It's just like this wave of fire and ash rolls past her, and her hair just kind of like flips or something. It's ridiculous. Anyways, I'm so sorry. Yeah. All right. Now, this is what happened in Pompeii. Are you all familiar with Pompeii?
I was gonna ask about that.
Have you ever seen the images of the people in Pompeii?
The casts.
Warning, may not be suitable for children. Okay.
Oh my goodness.
I think the wording was correct.
These are casts of people from the village of Pompeii. Also, by the way, Pompeii wasn't alone. The town of Herculaneum as well was destroyed in this eruption. Mount Vesuvius in 79 AD erupted in the middle of the night. If any of you are interested in watching a fun movie on the subject, Kit Harington was in one called Pompeii. It was actually a fun watch. I won't say it was a very good movie, but it was a fun watch. Okay. There are a few suspenseful moments, but I like Kit Harington, so I watched it, and it was enjoyable. Okay. In the middle of the night, the volcano erupts. Pyroclastic cloud leaves the volcano, flushes down the valley and into these towns, going so fast it's nearly instantaneous. People asleep in their beds, dogs in the middle of waking up or scratching themselves, children fast asleep, lovers with their arms around each other, someone just barely starting to get up. Maybe he heard something, maybe he needed to use the restroom. All in a moment, flash incinerated. And as their bodies were incinerated in those positions of death, that ash solidified into a solid layer of tuff around them, forever preserving an empty void in the exact shape that their bodies occupied the moment they were incinerated. Many, many, many years later, that happened in 79 AD. So in the 1800s, when archaeologists were going through Pompeii, digging down, and they found these weird voids, these weird holes, they didn't think anything of it until someone took out a chunk and realized that's a negative imprint of someone's body part, right? And then they started filling those voids with cement and then carving the tuff from around them. And that's when they realized all these empty spaces, those are in the shape of the bodies of the people. So that's what you're looking at here. You are looking at the casts of people, children, dogs, adults, families, living in their living room, wherever they slept. All the people and when and how they died in that brief moment of incineration. That's what a pyroclastic cloud does. Nope, that's the wrong. There we go. Let's bring this back up here. Why does it move so fast? Well, that gas is acting as an envelope. It is cutting the friction between this cloud of ash and everything else around it, including the atmosphere. And so this extremely hot fluid, gas is a fluid, is blasting through the atmosphere and through everything else, like literally a hot knife through butter. Okay? So we already watched that. Now let's talk about lahars. This is the next thing that could kill you. A lahar. When you look at a volcano, you're often going to see it covered in what? It's made out of rock. But what's it covered in? It hasn't erupted yet. When you look at this volcano, what's it covered in?
Snow.
Snow, ice. Most of them are so tall that, at least to some extent, they have a lot of snow, ice, glaciers on them. Okay? So, what happens if my magma is moving up? This thing's getting ready to explode. Magma's moving slowly up closer to the surface. Yeah, the temperature of my volcano is going to increase, and along with that comes a lot of melted ice. Where's that melted ice going to go? Downhill. Yes. On its way to join all the other water on its way to the ocean. It's probably going to flow down wherever streams or rivers, nearby rivers go. It's going to follow natural low points to try and reach an area where it's no longer being forced downhill, just like all water does. Okay? And as it goes, this massive quantity of water just sloughing off the side of this heating up volcano, it's going to pick up trees and houses and bridges and cars and towns and people and sweep them all the way downstream too. That is a lahar. Okay? This is the aftermath of a lahar. This is a stream bed. Look at the size of these trees compared to this person. And look how high the water line was in this forest. Yeah. Ripped up trees so wide, it would probably take 3 of us holding hands to reach around it. Okay? That's an incredible amount of power. Sweeps away towns and villages. In Colombia, I forget exactly what year, but there was a town called Nevado del Ruiz. You did? Perfect. Do you remember the year? That sounds about right. Yeah, I'd love it if you could look it up and let me know. I keep meaning to put the year on here, but I always forget at the end of every lecture. I get distracted. 1985. Perfect. Well done. Thank you. Appreciate that. I will try and remember to add that on here next for my next class. But this is a volcano that erupted, and the volcano itself wasn't even a huge threat. What was a threat was the fact that this town was on the side of a river that was fed by the glaciers from this volcano. And so the lahar swept down the river and killed 25,000 people. Yeah. Yeah, I rounded, but yeah.
That's from all the ice and the snow.
The ice and snow that melted, flushed downhill, and swept it all away.
They're like places that were far from volcanoes.
A place in the world far from volcanoes? Yeah, where you are right now. You're good. Volcanoes are not a problem here. Not anymore, anyway. There have been some here in the past, but not anymore. Long time ago. There may be some in the future, but I'll talk about that later. Okay? Okay, now, I used to live at the base of a mountain called Mount Rainier. That's actually this one right here. Y'all recognize what this picture is of? Seattle. It is Seattle. Yes, this is a picture of Seattle with Mount Rainier in the background. Fairly close. I used to live at a town called Ording, right near the base. Okay, very close. Okay, and this town is in the valley near the bottom of the volcano, and there's a river that comes down off the volcano. It's fed by those glaciers. It runs through the town, right next to the town, okay? There are 3 ways out of this town. One that goes up to the volcano, one that goes down the valley following the stream, and one that crosses the stream with a bridge and goes up the side of the valley. On the first Monday of every month, every siren in the city starts going off. Right? Why? Because this is a Lahar drill. Every single person in that city, there's about 8,000 people when I used to live there. Every single one of those 8,000 people is supposed to practice picking up their stuff, getting their kids, and getting out of Dodge. Leave. Now, are you going to want to go towards the volcano if there's a Lahar? No. Are you going to want to go down the valley next to the river if there's a Lahar? No. So there's only one way out, and it's to cross the bridge over the river and go up the side of the valley. How many of those 8,000 people do you think practice leaving town over that one bridge to get out of town in the 12 minutes it would take before a Lahar goes from the volcano to the city? No one. We hear the sirens and everyone keeps going about their business. No one practices because 8,000 people know that 12 minutes is not enough time for them to get out. That's 8,000 people who know that if it happens, they're just dead. That is one example of many cities in such situations, okay, where cities were established long before we understood natural disasters and the consequences. Should a Lahar ever happen, that city is gone, along with several others in the area. Matter of fact, only an hour or so later, that Lahar would sweep into Seattle. Seattle is built on top of the last Lahar deposit next to the river, where it empties into Puget Sound. So far, yeah. In recorded history, the one in Colombia was the biggest one. Yeah. There's always the potential for a new record, though, isn't there? Yeah. So if that happens, half of this city is just gone. Half of Seattle would just be swept away, probably rendering the other half uninhabitable, right? So these are reasons why we go into such depth to study these things and understand these things. Beginning to understand the depth of the consequences of these things. By the way, let's talk about ash for a minute, in case I didn't give you enough nightmares. Here is some Mount St. Helens ash. I'll pass this around. Okay, this is ash. Very, very fine powder. But each single grain of this powder is a tiny shard of glass. That's what ash is. It is glass. What happens if you breathe in ash, these microscopic pieces of glass? It slices up your lungs on the inside. And it's really hot. And you drown in your own body fluids from the inside. Yes. So, if you are ever in a situation where volcanic ash is floating down, don't breathe it in. Cover your mouth, even just with your shirt. Okay? Just be safe. All right? All right. Any questions about volcano-related disasters?
Isn't there like sulfur storms in like volcanoes, something like that?
Sulfur storms.
Or like I don't know how it is.
Are you talking about like lightning storms? There's often a lightning storm associated with volcanic eruptions because all the ash in the atmosphere is creating friction and making lightning. Is that what you're talking about?
No, like sulfur gas from like the volcano like comes up every once in a while.
Sulfur dioxide is one of the most common gases as a byproduct of volcanic eruption, yeah. But
Because I know some people go down into volcanoes and they have to worry about sulfur.
yeah, sulfur dioxide is one of the gases that escapes. And so you definitely want to have a breathing apparatus when you go anywhere near an active volcano. Otherwise, you could suffocate. Yeah. But a sulfur storm.
It comes every like few hours and whatnot, like where sulfur gases.
Well, so sulfur dioxide from a volcanic eruption can get into the atmosphere and then make a sort of sulfuric acid in the rain. That's often, there's usually some form of acid rain associated with the gases from volcanic eruption. Is that what you're talking about,
I
maybe?
think so.
Yeah, it's not as dangerous as a lot of people think. Yeah, it's poisonous and you wouldn't want to drink it, and it'll probably kill a lot of like the plant life in the area, but it's not going to like dissolve your car, right? They play up acid rain a lot in movies and stuff. Yeah.
I was wondering, like, have you been near like any other active volcanoes aside from the one in Seattle?
Yes, I've actually climbed Eyjafjallajökull in Iceland while it was erupting.
Which one?
Eyjafjallajökull in Iceland. Back in, when was this? 2013, I think it was. It erupted and it shut down air traffic across half of Europe because of all the ash it put in the atmosphere. And then in 2017, I went to visit it while it was erupting again, and I hiked up the side of it. It was really fun. I actually took my wife on that one. Wait,
How many like miles?
a couple miles up. Like, I mean, it's not a couple miles high, but you know, a couple miles all around, like on the side of that volcano, going back and forth. Yeah. All right. So, calderas. A caldera is what happens when you have a very large empty space left behind that a volcanic structure once occupied. For example, Yellowstone has a 15-mile wide or kilometer miles. I believe it's 15 kilometers wide caldera. Okay, from the last time it erupted, a lot of it blew up. Same thing with Crater Lake. The volcano that once sat where Crater Lake is now blew up big, went kaboom. It's such a powerful, immolating eruption that it emptied a whole bunch of its magma chamber in this eruption. Just boom in this massive eruption, leaving a big empty space underground. And the rest of the volcano on the surface kind of collapsed down into it, leaving a giant depression on the surface, which got filled with water and is now what we call Crater Lake. Crater Lake is not, contrary to a lot of popular belief, the result of an impact crater. It's not from an asteroid. It's from a giant volcanic eruption. Okay. Fissure eruptions. A fissure eruption is what happens when magma comes up through a crack in the ground, a long crack in the ground, versus one single conduit that will make a volcano. Every now and then, because there are lots of cracks in Earth's crust, that magma will find its way up through one of those cracks, and when it does, it starts spitting lava out in this along this linear feature instead of just in one location. Okay, and that will make what we call basalt plateaus. There's a lot of these in Idaho and Montana. Okay. Lots of basalt plateaus. There's a lot of these there's a huge one in India. There's some in Siberia. Okay, there's lots of them all over the place, where there's lots and lots and lots of basalt that just gets spread far and wide. A lava dome is what happens when your volcano erupts, and then most of the pressure is gone, but every now and then a little bit of pressure will force some more lava up. It'll push that material up and it'll cool off near the surface because there's not quite enough pressure for it to make an eruption. So this is Mount St. Helens now, post-eruption, right? Obviously. What do you see in the middle? You see this? It's like a cute little baby volcano. Yeah, isn't that cute? Growing in the middle of the older one, right? And yeah, it does do a little, it spits out steam every now and then. It'll have a tiny little eruption. But what's happening here is a little bit of material gets forced out, it spits out a little bit, has a little eruption, and over time it's gradually building up this new volcano inside the old one. We call that a lava dome. Think of it as kind of a new cork on top of the conduit. Okay? But what happens when your volcano is long dead and it's broken down and weathered away? It's so old that all the outer layers of your volcano have gotten weathered away by wind and rain and the long influence of time. Okay? Normally, the rock that forms from the magma in your conduit is harder and more resilient than the rock that formed on the outside of your volcano. And so you're left behind with what we call volcanic pipes. What you're looking at here is effectively the conduit or a piece of the magma chamber from a volcano that used to exist around it. Imagine a long time ago, there was a big old volcano here somewhere above this feature, it's not there anymore. It's so old that it got broken down and weathered away. But because the rock that came from the magma that cooled inside of that structure is harder, more resilient to weathering, it is still there. Okay. Now, a lot of our volcanoes happen around the Ring of Fire. We already talked about why. A lot of these tectonic plate interactions, right? Convergent, divergent plates. Every now and then, one will occur inside of a plate. Can someone give me an example of volcanoes that occur inside of plates instead of on the edges? Any ideas? Do you see any on this map? Huh? Mount St. Helens is here. It's right there in that border. I'm talking about something inside of a plate, not on the edge.
What was the question again?
Can you tell me a volcano that is not on the Ring of Fire or not near a tectonic plate boundary? It is inside of a plate. Mauna and Kilauea, Hawaii, nowhere near a plate boundary. It's smack dab in the middle of our Pacific plate. Why is it there? There's no tectonic plate boundary causing it to change. There's no convergence introducing friction. There's no water entering the mantle there. Why is there a volcano or several volcanoes there? Any ideas?
Came from underground?
It definitely did. Why is there a volcano here in the middle of the Pacific plate?
Another eruption.
Yes, it is erupting, but why at all? Let's review real quick. We have convergent volcanism, when one plate dives under the other, introducing friction, or water if it's an oceanic plate, right? That water comes up here, reduces the melting point of our mantle rock. That mantle rock becomes magma. The magma comes up through the crust, and you get volcanoes along that convergent plate boundary. You have divergent volcanism, where two plates are splitting apart from each other, making new space, new rock between them, and where they are thinnest, there at that point, there's this thin area where the pressure is less, and because the pressure is less, the mantle there can be in a melted state, and that's what's feeding the divergent volcanism there. But in the middle of our plates, there's got to be something else.
It's not that the plate's breaking, right?
No, it's not breaking. This is called intraplate volcanism. We most often call these hotspots. You all done? Anyone else want to hold Diablo today? Okay, Angel wants him. All right. These are called hotspots. Now, let's go back to our good old friend, the lava lamp. Here's our mantle, our core, our outer core. It's our main heat source for the mantle, right? As mantle material gets hot on the outer surface of the core, it's going to lose its density and therefore start to rise through the mantle until it reaches the bottom of the crust. Who says that has to happen only at plate boundaries? No one says that. Okay? If some piece of mantle gets really, really hot, I'm talking about a piece of the lowest part of the mantle, right there next to the core, so hot, and then detaches, and then over the course of millions of years makes it up to the surface, under the crust. At those lower temperatures, it can be melted. And so you get this pool of magma that's underneath. It's just pooling there under the crust. And wherever that is, inside of a plate or on the edge of a plate, it's going to gradually chew its way up through the crust and make volcanoes. We call that a hotspot. Okay? Some common hotspots that you may know about: Hawaii. Also, where's Yellowstone? Is it near a plate boundary? No. Yellowstone's over here in the middle of North America. That's also a hotspot. Okay? There are several of them. A lot of them, actually. Okay? So this is just a diagram that shows you, again, it's kind of a recap image of a lot of the things we talked about today. So we've got divergent volcanism, where plates are splitting apart. And by the way, when a new divergent plate boundary is forming inside of a continent that makes what's called a rift valley, it splits continents apart. You're all probably familiar with the fact that South America and Africa used to be connected at one point. They fit together like puzzle pieces. Why'd they split apart? This divergent plate boundary that we now call the South Atlantic Ridge right here. Okay, so here's the Mid-Atlantic Ridge, the North Mid-Atlantic Ridge. Here's the South Mid-Atlantic Ridge. Okay, it did not start there. It did not start here with all this ocean. It started by splitting these two continents. They are two continents now. They were one before, apart. That is currently also happening right here. This East African Rift Valley, you can see on this image and every map of Africa that you look at, right? You see all those valleys and mountains. That is currently splitting Africa apart. Give it another 50, 60 million years, there will be ocean here, and we will have a whole new subcontinent here we call East Africa. Okay? We'll call that West Africa, and this will be East Africa. Okay? And then we've got fissure eruptions here. We've got divergent plate boundaries in the ocean. This shows you how convergent volcanism between two ocean plates works. Hot spots right here, convergent volcanism between an ocean and a continental plate. This image just kind of breaks it all down for you in a very convenient way. It gives you a graphical representation of each of the things we've talked about. Okay? All right, so how do we live with these things? We've talked at length about why we should be very cautionary around volcanoes. Well, we can't live our whole lives without going near them because they're all over the place. That would severely limit the number of places we could live. So we got to figure out, we got to figure out exactly how we can coexist, I guess you could say, with these things. So we monitor them. We pay very close attention to them, and we constantly study them so we can try and figure out better methods of forecasting when they possibly could erupt. We don't really like to use the word prediction. Prediction sounds almost too, I don't know, astrological, you know, like using the stars to predict your future sort of stuff. We don't like using the word prediction. We prefer forecasting. Forecasting uses data to try and figure out a likely outcome. That's what we do, okay? So we do things like monitor gas output. We have infrared sensors to determine, is it expanding? Also, is its temperature increasing? All of these things, okay? There are even satellites dedicated to watching some of the more threatening volcanoes. For example, Mount Rainier, if that thing goes, millions of people are threatened, right? And so they watch that extremely closely, okay? Also, earthquakes can be a good indicator. So there are seismograph stations, which we'll talk about here in a few weeks, set up near a lot of these volcanoes. As the magma is approaching the surface while your volcano is getting ready to erupt, that magma is going to be displacing rock that was there already. And it's going to cause cracks and breaks and movements in the crust, and those will manifest as small earthquakes. So oftentimes, whenever we see earthquakes swarming, which is a whole bunch of little earthquakes under a volcano, that usually means there's magma rising. Okay, so we monitor all these things to try and keep the public as safe as possible. And it's usually organizations like the USGS that do that. Any questions about our lecture today? What did you think? Was it fun? Very interesting? I will take that. I will happily take interesting. All right, I'm going to give you just a quick breakdown of your lab. It shouldn't take that long. The format exactly follows that of Lab 1. Okay, so you are still going to be doing identification. The only difference really is that you're doing it with igneous rocks this time, instead of minerals. And you're collecting different properties based on, you know, what kind of rock it is. And there are only 12 samples instead of 24. No, it's not bad at all. Especially after having done 24 for Lab 1, 12 should be like a breeze, right? Okay, So
Does that mean that they're going to be harder to identify?
no, I will not say that the hardness level of this has increased. I'd say that the difficulty level has stayed constant, but you have half as many to do.
Works for me.
Sound fair? All right. So just remember, your compositions are what your rocks are made out of. And by the way, if in any other literature, if you choose to do your own research for this, which is totally fine, sometimes you'll see the word silicic used in some material. Silicic means the same thing as felsic as far as my class is concerned. Okay? Other authors, other scientists may use those as different things, but as far as you are concerned in my class, they mean the same thing. Silicic and felsic are synonymous. Okay? So your different textures you're going to be identifying. What are those textures? Well, remember you've got your aphanitic textures. We learned this last time, right? Aphanitic, fine-grained, microscopic crystals formed quickly on or near the surface. That's what that means. Phaneritic, large crystals, less than 2 millimeters in size, or 2 centimeters in size, just, so we can keep things straight here, but large enough to see with the naked eye. Phaneritic, formed slowly underground. Porphyritic, it's a combination of the two because there was some partial melting involved here. Glassy, it was quenched instantly, like that. Nothing but silicon tetrahedrons had time to form. Pyroclastic, the result of a volcanic eruption. Pegmatite, that's what we call a type of rock with crystals larger than 2 centimeters because they was formed near the end of a magma chamber's life cycle. Okay, so what are we going to be doing for your lab? You're going to be finding properties like, do you see quartz? What's the percentage of ferromagnesian minerals? What's its composition, right? What's its texture? These are things that you're going to be identifying. All these things we talked about in the last 2 lectures that will help you be able to identify what those minerals are. Or not minerals, sorry, what those rocks are. Same thing for as for lab 1. You're going to be following the same process. You are going to be observing each one of these, collecting the properties I asked for on the assignment. After you have found the properties, you're going to open up that Excel spreadsheet. You're going to try and find a match using the properties. Don't try to match pictures. Match properties. That'll get you there so much more often than trying to match pictures will. Okay? After you have matched your properties, then if you want to double check, you can go to, for my in-person students, the back of the room, and you can find the practice samples back there and see if it looks like what you've got or if it has the same properties. Okay? For my online students who watch this later, you can use the videos on my YouTube channel for the practice set for lab 2, and you can compare those to what you've got as well. Okay? Any questions on this lab? Good.
Pretty straightforward.
Oh, she's back. You stop talking about her now. Sorry. I'm just kidding. I'm just kidding. All right. I'm going to end it here.
Sharp, man.
Absolutely.